So when the bubbles of the d orbital points towards the negative charge of ligands, it's not happy.
That's right.
You have only 2 of them.
And there's only 2 where it's pointing directly at the corners.
Okay, the same. It's not happy.
Whereas there's 3 sets of d orbitals that are where all the bubbles, all the lobes, I should call them, all the lobes are pointing between the corners towards the edges of the octahedron.
So it's dxy, dzy?
Yeah, these 2 high energy ones were called the dz squared and the dx squared minus y squared, and then the low energy ones were called the dxy, the dyz, and the dxz. But I didn't get the sense that your instructor expects you to have this memorized, or maybe even to be able to figure this out. I wanted to go over this in order to try to make this make a little bit more sense. But the main thing we want to focus on is how to use this, not how to derive this.
So,
I think most of the problems you'll see will be about how to use this. So I don't think you'll need to memorize that these d orbitals. At most, if you're given one of these pictures, you should be able to point out which are the high energy and which are the low energy by seeing where the lobes are pointing towards the corners and where they're not. But the way this is usually tested in this type of introductory course is just how do we use this, not how do we prove it. So I wanted to show how to prove it so we get a little bit more understanding, but that's not the key.
So that's how we should draw now d orbital for the future. It means that we need to put lower energy and higher energy.
For these transition complexes.
Yeah,
that's right.
Complexes.
That's
so
right.
We put 3 down and 2 up.
That's right.
Okay.
Well, that's how you draw it for the octahedral transition complexes. Mm-hmm. It might be different for the tetrahedral, say, or the square planar, because we were working with octahedron pictures here, right? Yeah. So all we've done so far is the octahedral case, but we're starting with that because that's by far the most important for this course. We'll talk much more briefly about the other cases when we're done. But most of the problems you'll see will be about the octahedral case, so we'll start by focusing on this. So this is how you should draw the d orbitals for the octahedral case for these transition metal complexes.
It still can make sense, like, without even, I mean, even if we have square, we can still figure out based on this. Okay.
Right. Okay. All right, so I'll erase these names, because like I said, that's not too important, I think, for this course. They actually have names for these 2 levels. The high energy level is called E sub G, and the low energy level is called T sub 2G. I don't know where those come from. I don't think that's too important either, but for completeness, I mentioned that there's just names for these 2 different levels. These names wouldn't apply to the free atom because there's only 1 level for the free atom. By the way, maybe I should have said that the free atom maybe I should have drawn down here, because the free atom, all of the orbitals are happier than here. Even these are not that happy because even though they're not pointing straight at the ligands, they're still in the vicinity of the ligands. So the free atom would be happiest because then the lone pairs wouldn't be close to the ligands at all. So both of these are higher energy. It's just that the increase in energy is bigger when you're pointing straight to a ligand than when the lobes are pointing between the ligands.
One more question.
Yeah.
So just to make free atoms, free d orbital we draw only for neutral compounds from transition metals. Yeah.
I mean, so a free d atom. The free case would just be, say, if you just had neutral iron by itself. That's right.
Then if we have ligands, we go up to this.
Then you do this.
Okay.
Yes,
okay.
That's right. So we've been talking about the free atoms just as kind of a reference case. But in this chapter, we actually don't focus on the neutral free atoms very much. We focus more on the cations in the complexes.
Okay, that makes sense.
Okay, so we've seen that there's now splitting between these 2 levels. However, it turns out that sometimes there's a big difference between these levels, and sometimes there's only a small difference between the 2 energy levels, depending on how unhappy you are to be close to those ligands. This distance here is called delta. Delta is the difference in energy between the 2 levels. Maybe it would be better to call it delta E, because it's the difference in energy, but the convention is this is just called delta. Well, what we just said is that you might have a big delta or a small delta, depending on the particular type of complex you're dealing with. Some of the complexes have big deltas and some have small deltas. This phenomenon is, so we've been talking here about what's called the splitting of the d orbital energies. So here's the splitting of the d orbital energies. Well, some have large splitting and some have small splitting. This is called the strong field case. And this is called the weak field case.